Okay, so have you ever actually stopped to think about how simple electrical signals, literally just on and off, ones and zeros, how they somehow manage to create the entire complex digital world around us? I mean, from the quick text messages you send to those incredibly vibrant video games you play, all the way up to massive artificial intelligence models. It all boils down to the exact same microscopic foundation. But how exactly does that translation even happen?
Well, welcome to this explainer. Today, we're going to demystify the absolute core concepts of the AP Computer Science Principles curriculum. Whether you're actively gearing up for the exam, or honestly, you just want a rock-solid understanding of how computers actually think, you are in exactly the right place. Okay, let's dive into this.
To make sure we grasp everything perfectly, here's our quick roadmap for today. First, we'll cover speaking ones and zeros, then data in the real world, followed by lists, loops, and logic. After that, we'll check out the robot navigation guide, and finally, wrap up with avoiding common exam traps. Let's get right to it.
All right, Section 1, Speaking Ones and Zeros, the foundation of binary.
So at the absolute most fundamental level, a computer only understands a bit. And a bit is really just a 0 or a 1. That's it. But by grouping these bits together, we suddenly unlock the ability to represent much more complex numbers. The golden rule here is pretty simple. N bits can represent 2 to the power of n different values. So for example, 4 bits gives us 16 possible values, and those range from 0 to 15. If we double that capacity to 8 bits, we get 2 to the power of 8, which is 256 values, ranging from 0 to 255. Now, to translate that into a regular decimal number that we humans actually understand, you literally just add up the place values wherever there happens to be a 1. So if you're looking at the binary number 01001011, you just add 64 plus 8 plus 2 plus 1, and that perfectly equals 75.
Now here is a really cool mathematical cheat code that's built right into the binary system. Just like adding a 0 to the right side of a normal, base 10 number multiplies it by 10, adding a 0 to the right of a binary number instantly multiplies its value by 2. It's that easy. For example, the binary number 1010 equals the decimal number 10. If we just slap a 0 onto the right to make it 10100, the value instantly doubles to 20. Add 3 zeros to the right and you're multiplying by 2 to the power of 3, meaning you just multiplied the total value by 8.
But this system isn't completely bulletproof. It has very real physical limits. And that brings us to 2 major numerical limitations you absolutely must know. First up, overflow errors. Overflow happens when a calculation spits out a result that is just way too large for the allocated number of bits to hold. Think of it like trying to pour a whole gallon of water into a tiny coffee mug. If you only have 4 bits, your maximum possible value is 15. So if you try to add 14 plus 15, you get 29. The computer physically cannot store the number 29 in just 4 bits, so it literally overflows. Actually, fun fact, overflow is exactly why super old video games would suddenly glitch out or reset your score to 0 if you got too many points. On the flip side, we have round-off errors. This is what we call a floating point precision issue. Basically, computers sometimes struggle to perfectly represent certain decimal fractions using binary, so they're forced to approximate them. That's exactly why a computer might calculate 0.1 plus 0.2 and hand you an incredibly messy answer like 0.300000004 instead of a nice clean 0.3. It's not broken, it's just doing its best to round off to the nearest fraction it can physically represent.
Okay, moving right along to Section 2, Data in the Real World, translating numbers to reality.
So, how does a computer actually know that you're texting a smiley face or typing out a letter? To represent text, computers use something called ASCII, which simply maps specific numbers directly to specific characters. For instance, the decimal number 86 will always represent the capital letter V. For colors, computers use the RGB system, which blends red, green, and blue values together. So the color indigo is mapped perfectly as 75 red, 0 green, and 130 blue. And what about the music you stream or the voice notes you send your friends? That continuous, real-world analog data is basically sampled at regular intervals, and every single one of those samples is stored as bits. The more frequently you take a sample, and the higher the bit rate, the much better the digital quality is going to be.
But because all that high-quality data takes up a massive amount of space, we have to compress it. Let's quickly compare the 2 main ways we do this. Lossy compression literally shrinks the file size by permanently throwing away some of the original information. Usually it targets data that human eyes or ears can't easily perceive anyway, like super slight color variations in a photograph. On the other hand, lossless compression acts a lot more like a zip file. It drastically shrinks the data footprint, but without losing a single bit of the original information, which means you can reconstruct the file perfectly later.
All right, let's look at Section 3, Lists, Loops, and Logic, Building Digital Instructions. Okay, pause. Please listen closely to this one, because it is a crucial quirk you absolutely must memorize for the exam. Unlike almost every single major standard programming language out there, like Python or Java, which start counting at 0, the AP Computer Science Principle pseudocode starts its list indexing at 1. Let me repeat that. Indexing starts at 1. If you have a list containing the words red, green, and orange, the item sitting at index 1 is red. Do not forget this trap, or it is going to completely throw off your code tracing.
Now, let's take a look at a classic example of a nested loop. Basically a loop right inside another loop. Imagine a block of code that says, for each x in list x, and then, tucked inside of that, for each y in list y. This kind of structure is incredibly useful for searching and comparing two totally separate lists. What the algorithm does is it checks the very first item in list x against every single item over in list y. If it finds a match, where x perfectly equals y, it appends that item to a brand new list. Once it finishes that, it simply moves to the second item in list x and starts the whole matching process all over again.
Next up is another massive tool for your logic toolkit, the mod operator. I know, it sounds super complex and mathematical, but honestly, it's just an operation that gives you the remainder of a division problem. That's all. If you take 10 mod 3, your answer is 1. Why? Because 3 goes into 10 exactly 3 times, which leaves you a remainder of 1. Now, why do we even care about this? Because mod is quite literally the ultimate way to test divisibility. It's exactly how your favorite music app's playlist knows when it needs to loop back to the start, or how a program easily sorts even and odd numbers. Because think about it, any even number, mod 2, is always going to equal 0. So when we want a program to repeat certain instructions, we rely on loops. A repeat n times loop is pretty straightforward. It runs an exact predetermined number of times and then stops. But a repeat until loop? That one keeps going until a very specific condition becomes true. And you have to be incredibly careful here. If your logic is somehow flawed and that condition never, ever becomes true, yikes, the program is going to get completely stuck in an infinite loop. It'll just keep running endlessly until the whole system crashes or the user forces it to quit. Of course, to control all those loops, you need gatekeepers. Enter Boolean logic. These specific operators evaluate down to exactly one of two possible values, true or false. If you master your equals, not equals, your less thans, and your greater thans, you basically master the flow of the entire algorithm. They are literally the ultimate decision makers in any piece of software.
Next is Section 4, the Robot Navigation Guide, Moving in the Physical World.
A huge part of truly understanding algorithms is being able to trace how a robot navigates a grid. And to pull this off without making silly mistakes, you really need a disciplined mental sequence. Step 1, pinpoint the exact starting position. Step 2, and honestly, this is where most people completely mess up, identify the starting direction the robot is facing. Step 3, carefully track any rotations left or right. Step 4, track the forward movements. And finally, Step 5, always keep an eye out for walls and obstacles that might block the robot's path.
Now, the good news is, in the AP CSP framework, you only have to worry about 3 specific commands to execute all that navigation. Move_forward, rotate left, and rotate right. And remember, rotating does not move the robot into a new square. It simply changes the direction it happens to be facing inside its current square. Keep your state tracked meticulously, step by step, and these grid problems become an absolute breeze, for sure. Finally, Section 5, Avoiding Common Exam Traps, your survival guide.
Okay, let's really lock this in before test day. Here is your rapid-fire survival checklist. Number 1, AP CSP list indexing always starts at 1. Number 2, 4 bits gives you 16 total values, but the absolute maximum number is 15, so do not fall for the 16 trap. Number 3, 8 bits represent the values 0 through 255. Number 4, know your errors. Overflow means the calculated number is physically way too large for the allocated bits, whereas round-off is just an approximation issue dealing with decimal precision. And lastly, never forget your math cheat code. Adding zeros to the right of a binary number instantly multiplies it by powers of 2.
Understanding these foundational rules genuinely gives you the power to see exactly how computers process our reality. But, it also raises a pretty fascinating thought.
If just 8 tiny bits can hold 256 values, and 32 bits can hold well over 4 billion, what physical or mathematical limits are we going to hit next as our world inevitably demands infinitely more data and infinitely more precision? It kind of makes you wonder, right? Keep exploring, keep questioning, and you will absolutely be well on your way to mastering the digital universe. Thank you so much for joining me for this explainer. Keep up the great work.